Today we continue our exploration of the application layer, which will be an opportunity to also discover how it can be used to solve the IPv4 with IPv6 interworking issue, a topic that will keep us busy for this and the coming 3 weeks. We left on this slide last week. That is a one-slide explanation of how DNS works. The main take-home message is that the local DNS server to which you connect in principle provides you a recursive service. That means it will help you with the final answer, but all other DNS servers in principle don't do that. And the way DNS queries are resolved is by having every server know what is just below its level. For example, the server on the right here, the root name server, knows only the IP address of a DNS server for IBM.com. The server IBM.com will know about all IP addresses of everything inside IBM, for example, or if IBM itself is separated into subdomains, it would then know what are the IP addresses of the DNS servers for those subdomains. This is the main thing we've seen. If we compare to a database system, we can view the DNS as a big worldwide database that has all the IP addresses that correspond to all the names. If we compare to a database system, we will see there is a major difference that has to do with this field here, the time to live. What is this field? Well, this is, for example, when the answer has come from watson.ibm.com, this time to live, which is a time in seconds, here 7,200 is 2 hours, means that's the time that all other DNS servers might keep this answer in their record. So when the EPFL web server has resolved an IBM address, it keeps it in its cache. So that when the next guy comes, here Bart, that also does the same because he always imitates Lisa, then he will get the answer directly from the cache. He does it 60 seconds later, therefore the time to live in the local web server is a bit different. And after 2 hours, this will expire. So if Bart would have come 2 hours later and nobody had done anything to the server in between, then the same thing will happen as Lisa did. So what we find is here something we have already encountered with ARP, it's a cache. The local server has done a lot of work throughout the world to know the answer, and it keeps the answer locally. Yes?
Is it possible to enforce not using the cache? Maybe if you know that the server changes the address for some reason and you don't want to use the cache in between?
Well, you can go directly to this one if you know the IP address, which you can with a bit of work. No, because you can go, whatever the server does here, you can do yourself with dig or tools, NSLookup, or write programs to do it. So you can do it, but by default, your machine won't do it. If we compare to a database system, the main difference is consistency. Now, there is not necessarily consistency between all the DNS servers in the world. There are the DNS servers that are at the source of information. They are called authoritative. Watson.ibm.com is authoritative. All the mappings, all the records concerning IBM that are in this server are, in principle, the correct ones. And if there are several IBM.com servers, they are synchronized by a database mechanism so that they're exactly the same. However, the EPFL the DNS server, is only a cache of that, so it has an information that might be a bit out of date, might not be the same as another cache. So that's the price to pay. As you know, databases are painful things that crash, that require a lot of processing and storage and everything, and a lot of maintenance and a complete dedicated people. DNS is much more lightweight at the price of not having complete consistency. In particular, if an address changes, there is no mechanism to flush the servers here. So if that address changes at IBM, for some time you will get the wrong address. And in principle, there's no mechanism to enforce that. If you know there has been an address change, you can get the right address. But if you're on the server side, you're changing the address, you have no mechanism to force all clients to go to the new correct address here. Sorry. I wanted to show also, those are examples of records that you can use with various tools. Here I use Dig. Another popular tool is Lookup. That's practically implemented in all systems. So here I've asked, for example, what is the A record for lca.epfl.ch. A records mean what's the IPv4 address. And here is the kind of information that is contained in the DNS. So the main information is that one that contains what is the IP address, but you have other things like canonical name. You have a large number of potential records. We won't discuss all of them. The only records of interest for us are A, quadruple A, and another one, the pointer record, we'll discuss a bit later. Canonical name is if you want to have several names for the same machine. Typically, servers like lca.epfl.ch, you are actually implemented on a given machine. If you change the machine, you may not give a name to the new machine, but in practice, that's very often done. System managers like to have names to the machines. So here, this lca.epfl.ch is in fact hosted by a machine which is lca1 srv2, which itself has an IP address which is given here. If I'm interested in the IPv6 address, I will ask for a quadruple A record, and I will get similar things, except now, of course, the addresses are IPv6, a bit more ugly. We've used the DNS already, actually it was the first lab of this course, implicitly when you did traceroute. Here, Lisa is doing traceroute to read more at beaglenetworks.net. And when you do traceroute, you get the names of all the intermediate hops. How does traceroute work? Who knows that?
The turn to leave, every time increase the turn to leave. And when the turn is expired, send the ICMP message.
Exactly. So traceroute will send, in fact, a UDP packet to a UDP port that is an echo port, or that is a dev null port on the remote machine with increasing TTLs. First with TTL equal 1, then TTL 2, etc. As long as the TTL is less than the value required to go to the destination, routers on the path will see there is a problem. I cannot forward this packet, the TTL expires. And many routers, not all, but many routers, when they see that, they send an error message, an ICMP error message back to the source. Your source machine now receives this error message. The error message, does it contain the name of the router? The DNS name of the router? Try to guess, yeah?
No, just
No.
contains the IP.
Just the IP address. So imagine you are a router, you don't put your names, everything. You just get a message that's wrong, you send it back, and by send it back, you just see in the IP message what is the source address. So the only thing that the traceroute program sees is the source address of who sent this error message. But now it displays the names, because people don't like IP addresses. With IPv4, we can live with our IP address. With IPv6, we really prefer names. How does it do it? Well, it uses what is called a reverse query, where we have now the reverse problem. The normal DNS problem is, here is a name, what is the IP address? Now I have the reverse problem. I have the IP address, find the name. How do you do that? How do you think that traceroute does the DNS lookup? Let's see the solution in 5 seconds. So 69%, which is a very clear majority, thinks that the DNS client asks the DNS server what is the name corresponding to this IP address, and the DNS server searches its database to find an answer. Well, that's a good answer, except if you're making a server, a DNS server. The correct answer is none of the above, in fact. So this is where the differential encoding will work. Why not? Why not answer 2? It's a performance issue. I mean, a DNS server is not as critical as a router, but still it belongs to the critical internet infrastructure. A DNS server will try to do things as simple as possible. That's why it uses UDP instead of TCP, and that's why most DNS servers are working in iterative mode. You ask a DNS server for something, it goes, finds a line, gets the answer, end of the story, forgets about you. Now, if you want to do this, the DNS server needs to go through all its database and find the name, which is perhaps possible, but certainly makes it very difficult to work with caches. That's the kind of things you do in databases. That's the kind of things that are very hard to do in a system which is locally cached. You really need to go to the root server, and that is something that the designers of the DNS said, no, don't do that, that's too risky. There will be way too much traffic on the DNS servers that are the authoritative servers. So that's not the way it's done, for performance reasons. So what is done instead? Good question. Which one? Here is what is done. In fact, it's a stupid thing, but like many things on the internet, in order to be simple and work, it's done in a relatively straightforward way. That's the easy part about this lecture. Then we put other records that do the reverse mappings. Those other records are called the pointer records. So in the DNS server, if you do it, it's not always done, but in principle, if you do it, you write records that go in the reverse directions, and they are called PTR records. And so, in some sense, we put, not in some sense, and to make this fit the general philosophy of the DNS, there is a domain invented called ARPA that contains a subdomain called in address, that is for IPv4 addresses. And then we consider that the address 128.178.151.1 is in fact a domain name that is the same in reverse order. And then you put the record that corresponds to this mapping in the DNS, so that when a DNS server asks what is do a reverse query, it is exactly the same mechanic as doing a direct query. In fact, you're doing a direct query on pointer records, hoping that they are present. If they're not present, then you will fail. You will say, I don't know. You will not search for the reverse query. You will just simply say it doesn't work. Here is what we can do, for example. If I try to find what is the name that corresponds to 128.178.15.1, which is an IP router of the backbone of EPFL. Then I find what are the typical, what is contained in the EPFL DNS server about this. There is this record is mapped to a name, which is given here. Now, if I do the reverse of the reverse, which should be the same as the direct query, I ask the DNS server, find me the IP address of this guy, then I go to another record, and hopefully the two are consistent, that gives me back the IP before address, which is what is illustrated here. In lab 1, we had funny things like the names that we found were things like Freedom to the Galaxy, for example. Do you think those are real DNS names? No, because you would need to buy the top-level domain called Galaxy. It will cost $500,000, so certainly they didn't do it. And the other names are obviously even worse. Right? They are completely bogus. So you can test whether they are real by redoing what traceroute did. What did traceroute do? Traceroute found an IP address that has sent this ICMP error message. So I ask the DNS system to give me the name, and if I do this, I do find something, and the something is Freedom to the Galaxy. So this is what is written in all DNS servers of the world. In passing, you see that there is no verification in DNS, in fact, whether the names are really valid names in the sense they belong to someone. Again, that's for performance. I mean, you put that in the DNS system. Whether the name .galaxy, the high-level domain .galaxy exists and is sold to you, this is not verified by the DNS servers here. So whoever owns those machines here has put into the DNS system bogus reverse pointers. They are bogus because if I try again, if I do a dig or a ping will automatically do a resolution. If I try to find what's the IP address that corresponds to this, I find an error message. So the other record is not present. So as you see, DNS works well, but you have to understand its limitations. It's, in particular, not necessarily authentic. The current DNS is therefore unsecure and has been unsecure for a long time. There is a proposal on the table to make it secure, which is partly implemented in some countries, not many. Sweden, I believe, implements it, but most countries don't, where the idea is to use a cryptographic public key infrastructure to force the authoritative sources to sign the records. So that if anybody, that would not solve the problem of Freedom to the Galaxy because they are authentically signed and they correspond to what the owners of this domain wanted you to believe. But this will prevent bogus intermediate servers to change the names. China, for example, systematically filters the DNS names, and the caches that are in some countries like China are manipulated and the names are changed. So if you go for some newspaper that contains topics that are forbidden in a given country, if the country is manipulating the DNS caches, it will point you to another site which has more government-friendly content. So this can be done because the caching occurs at EPFL. We could do that, right? We could, whenever we use in principle, the DNS, we go through the EPFL name server. So that would be a way to manipulate things. Of course, you have to make sure if you manipulate the DNS server that all your captive users have to go through this DNS server. You may remember in Turkey a few months ago, the government, which also is becoming more and more authoritative, was trying to prevent access to the internet. And then everybody went to DNS server of Google, 8.8.8.8, the one we use. And they did not know that by changing that, you get access. But next time they will know, and they will make it impossible for traffic to go to the 8.8.8.8. So DNSSEC will come probably in the future. It's a bit like IPv6. It makes sense to have it, but not everybody is interested in having it. In some other cases, you don't use DNS servers. For example, at home, if you have a printer, you give a name to the printer and you send a document to be printed to the printer. Probably it will find its way to the printer. Now, if we do that at EPFL with the printer infrastructure, you have print servers and Windows name systems that will take care of all that stuff. But at home, you probably don't do it. Instead, we use, in cases like this, something else, which is in the same philosophy as what we've seen for automatic address allocation in IPv6. Instead of using servers for address allocation or address resolution, or for discovering a mapping in general, we can always use broadcast. Instead of putting the answer, the mapping in a server, in a database or a loose database, we ask everyone. That's what we do with ARP. ARP is the same problem as DNS. I want to find the MAC address corresponding to an IP address. I change the IP address for a DNS name, it's the same problem. With ARP, we shout around who has this IP address. You can do the same with DNS. You can shout around who has the IP address corresponding to myprinter.me.athome. Then this has a protocol name, which is called Bonjour. From Apple, there were other versions like NetBIOS that was doing that before, but this one is the most popular one today. It doesn't do broadcast like I did, because broadcast is considered to be impolite today. You don't send things to everyone. Instead, of course, it uses a multicast address. But this is a link local multicast. So it won't work at home if your printer is not on your same local area network. If you have a complex network with routers, that won't work. So in practice, it works in one LAN. So that is still considered DNS, but is a serverless DNS. Assume that we change the IPv4 address of lca.epfl.ch. How much time will it take for the world to know about it? Let's see the solution in 5 seconds. And the majority is right. It might take up to 1 day because the TTL is this value, which corresponds to 1 day. So this value is set by whoever manages the DNS server that is authoritative for this domain. EPFL is fairly conservative. It says it's 1 day. What's the benefit of having a very long TTL?
Minimize the traffic to the authoritative DNS server.
It minimizes the traffic to the authoritative DNS server. So that reduces the traffic that goes to EPFL because you ask for something once per day, which for a server is minimal amount of work. Google is much more proactive. The Google servers have TTLs that are a few minutes, if I remember well. You can test it by using this or rather similar command. You can see the records that corresponds to any entry. Voilà, that's about the DNS, which is one of the most beautiful applications of the internet, although it's not a real application because it's used only for other applications. Yes?
If you have a TTL of 1 day and you want to be up 100% of the time, but still want to change your IP address, it means that you should keep the old IP address for 1 more day?
Exactly. It means someone else in the rest of the world trying to access you during 1 day might use the old IP address. So that's embarrassing, but that's a side effect. Now we move into topics that are really in the corners, but are very widespread, a bit like NATs. The application layer gateway is one of the topics. It's something that should not exist, but does, like many things, right? Like tax or etc. By definition, a gateway, an application layer gateway, or often gateway, is an intermediate system of the application layer. Intermediate system means something in the middle doing work for neither the source nor the destination. For example, when we use the web, normally we don't use gateways. Normally we go directly to the end, to the final web server. In fact, that's the typical case that shows how good the design of the internet was, because when the web was invented in 1992, we had to change, we didn't have to make gateways or whatever, it just existed if 2 people had the correct software on A and B here. However, in some cases we could imagine having a thing in the middle. A thing in the middle, if it's an application layer gateway, means it breaks the protocol into 2 pieces. The definition of an intermediate system is it participates in the protocol on the 2 ends. That means, for example, when A sends a GET message to a web server, the GET message, in fact, will be understood and obtained by the gateway, which means that the gateway will terminate the TCP connection, read through a socket like you did in the programming lab, read the GET, and then do something about it. If it's in the minimal case, what it will do is it will repeat it by opening another TCP connection to B, keep some state information, remembering A has asked me this, then ask it on behalf of A to B, hope that B gets an answer, and when B gets the answer, forward the answer back to A. This is what an application layer gateway does. In principle, it is stupid and completely useless, because without gateway, you get the same service. So if that's the case, then you don't do a gateway. There might be cases where you do it. A bit of terminology before seeing why. This is often called proxy as well. So the classical name you will find when you configure your browser is whether there is a web proxy. Proxy means here we do things on behalf of you. That's the general concept behind proxy. Why do we have web proxies or application layer gateways in general? Well, it depends. There are good and bad reasons. The bad reasons are the one that are such that the system works equally well without the gateway. Now, if you do a gateway, you have to have a good reason for that. One of them is sometimes to reduce traffic. A lot of the content is, or I should say, used to be the same. Now, more and more HTML pages are dynamic and created by the server at the time you log to it. But in the past, a lot of places used gateways to reduce the traffic with the same principle as the caches that we have seen for DNS or for ARP. With the idea that if somebody asks for some data that is acquired, for example, this is from Angola, so expensive link with bad performance, Then if you have a lot of space on your local machine, or if you're an operator that has a lot of servers and wants to give a good service, it might be a good idea to keep in your cache all the files, or files that are likely to be commonly asked again. What are those commonly asked files? Perhaps things like header files, a lot of decoration that you find on web pages that take a lot of space and are always the same. Then whenever someone else will ask for it, then it will get it directly from the cache, and you have a similar mechanism in HTTP and HTML to have a TTL. You have also more flexibility. You can ask for things and control whether you're happy with an old version or not. That's one example of an application layer gateway. Perhaps from a traffic performance, from a traffic viewpoint, congestion control viewpoint, we could imagine another reason. I mentioned here caching. Another reason could be that one of the two links is very bad. For example, this link might be a wireless link, and that link is a very, very long and relatively congested link. What happens if you go through a wireless link to something that is across the internet but congested? What might happen, or will happen most of the time? On the wireless link, you're likely to have losses that are not due to congestion, but your TCP will interpret those losses as congestion. Now, in the congested internet path, you're competing with the rest of the world that's trying to squeeze out a little of the capacity available here. But because your TCP believes that there are lots of losses, lots more than the others, you will get a much, much smaller share of this congested path. Plus, if your RTT is very large, we know that TCP has an additional negative bias against bad RTT, so you're likely to find very, very bad performance. And you can test this by, instead of going wireless, going wired, for example, through Ethernet to the same place, you are likely to find a much better performance, which contradicts apparently the principles of performance, which says that the performance is dictated by the bottleneck. The bottleneck is the congested link to Angola in that case, but the side effect of losses misinterpreted as congestion indicators cause problems. So a common solution to that is to make a web proxy here, because then you will separate the problem into two. You will have here a wired connection that will go to the rest of the world, and here between you and the EPFL cache you will have a high throughput connection with losses, but first the RTT will be small, and second, normally on wireless local links the throughput can be very high. So if you have a 50 megabit per second link to this local web server, the few losses that you have won't hurt you too much. You will very quickly have slow start that will move out of it very, very quickly. That's another reason, performance. The end-to-end principle is what captures formally what I mentioned informally so far. So one of the design principles of the internet, or one of the backwards engineered design principles, much of the internet was simply done. Right? Then after doing it, people wrote papers of why they did it this way and why it's a good idea, and they forgot about the things that didn't work. And so, but one of the things that did work is this one, the end-to-end principle, which we have seen under another occurrence at the beginning of the course when we said we use packet switching instead of store and forward. So that's just another name for the same thing. Packet switching is a fundamental idea that has made computer networking what it is today. We split information into small pieces that are all the same, and routers forward this information, which are all the same. So routers are fairly stupid animals that always do the same packet forwarding stuff. Because we have this, then since we have routers, we should not put store and forward things in the middle. So the end-to-end principle essentially says that application layer gateways are not necessary, should be avoided. However, it's not always applicable. Can you imagine cases where we would like to have application layer gateways? Okay, Can someone cite one reason? Yes?
Get around the firewall.
To get around the firewall, that's a fairly sophisticated reason. I agree, but the firewalls, let's talk about them later. Perhaps more basic stuff. Right?
Maybe protection of privacy.
Protection of privacy, that's a good reason. For example, when we see the application layer gateway used for web, then instead of having your web proxy simply forwarding everything to improve your performance, you can also check what's inside. And if there are URLs or files that contain words that you don't like kill Obama or things like this, then you might decide that you don't forward it to the user. So these are, this could be a reason. Any other reason? Yeah.
Load balancing.
Load balancing.
If you have a server and if you have multiple machines, you have just one point of access and it's just balancing around your servers to do computation.
Yes, though you have to make sure this machine. Yeah, that's a good point. But you have to usually play with the application to make the load balancing server not becoming the bottleneck. But there are more mundane reasons that you use every day. When you read mail, or when you send me an email, does your laptop send the email directly to my iPhone by the end-to-end principle? No, normally not. Why?
You need to store it somewhere. Maybe you, as soon as I send you an email, you won't be able to tell. You may see the email after a long time.
Exactly. So I may want, by the semantic of the application, I may want to store this information in a server that's available from multiple machines. So one of the reasons is the need to have persistent access to the data, or also mobility. At the time you send my mail, while I'm teaching here, my iPhone is not reachable. And so you may want to send a mail to me, even if we are not both at the same time active on the internet, which is required for the end-to-end principle. If I connect to a web server from this laptop, the web server is up and running and the laptop is up and running. If I send a mail, principle no. So a good reason for that is mobility, security, interworking, load balancing, performance. Lots of reasons have been invoked. Let me move on to firewalls. Are something that has been mentioned several times. There are constructions that are used to break the end-to-end principle, in fact. So what is a firewall? In general, a firewall is something that prevents fire from going from one house to the next in places where houses are made of wood. Right? That's the original meaning. So here, the fire is worms, virus attacks, and what you want is that hopefully your firewall protects your beloved intranet from all the bad things that happen over the internet. In practice, what is it? Well, in practice, we can think of a firewall as doing this. A firewall is typically made of filtering routers. In the BGP lab, you've seen that we can go to the router and make a number of rules. Well, we can do similar rules for simply packet filtering, lower level than BGP. Packet filtering means things like this here. We can instruct the router to kill some of the traffic that we don't like. In principle, if we obey to the dogma of TCP/IP, a router looks only at IP headers. So in practice, we should do that by looking only at IP headers. But of course, it costs nothing to look beyond the IP header into things like the TCP port number, if there is a TCP port number. So in practice, this is done. We've seen the same trick used in NATs. So filtering rules have to do with the addresses, for example, here destination address, but also the ports usually. So here is, for example, a rule in the filtering router that says anything that goes to that machine, 9.2, has a source port, something that is a typically non-reserved port, so used by a client, goes to destination 80, web server, is permitted. And there is another rule that says *** deny. So here we have a bank type firewall that forbids everything that is not explicitly allowed. So this router will allow very little. It will allow only traffic that goes to a few designated machines for a few designated ports. This is practically done everywhere in all boundaries between all private networks and public networks. There's practically no company today that opens entirely its network to the internet, like you can have when you're at home and you access Swisscom or Sunrise network. Even at EPFL, there is a firewall between EPFL and the rest of the world. If you set up a web server on your machine and try to access it from the outside, it will work because web servers are allowed. But if you make the lab, for example, you make one of the server programs we did in the lab on your machine at EPFL, you try to access it from another machine at home, it won't work. The traffic will not satisfy those rules. So one of the elements of a firewall are filtering, which if you want to be very strict, you filter at both ends. And then in between, you put machines that act as application layer gateways. We will see perhaps in 2 weeks they can act also as transport layer gateways. But most of the cases, what they do is application layer gateways. For example, if what is very often done is to put a web proxy, which means that anybody inside the company that wants to go to the web will not be able to go to the web because the first router here will kill all traffic that is HTTP and doesn't go to the proxy. So that won't work. You have to go to the proxy, and in the proxy we will take a log of everything that you're doing. So we'll know all the web pages that you've visited, and we might forbid you to go shopping on Le Shop during office hours, for example. Similarly, and perhaps more importantly, in the reverse direction, we want to avoid traffic to go to machines that are typically not in this yellow zone, which is called the DMZ, demilitarized zone, the zone where things are, in fact it's very militarized, but where we put machines that are expected to be very safe. Why that? Yes?
Because we cannot discover the network, and so we cannot. It would be easier for an attack to be done if we know how the network is.
So the reason you invoke is to avoid giving the capability to an outside attacker to discover your network. And what's the interest of discovering a network is to discover a machine that has one port open because it has not been properly patched, or so my Windows machine perhaps is not entirely safe and somebody could come and install malware into my machine in order, so we make this not impossible but more difficult because people from the outside cannot even see what's inside, and even if they would see it, they cannot access it. Of course, that's assumed that the yellow stuff is completely secure and free of all possible bugs, which you can never be sure, of course. But still, it mitigates the problem by saying those are the things you need to watch very, very carefully. So at EPFL, we cannot watch the thousands of PCs and devices that are connected to the network, but we can watch those things and screen them. This is another example where we will use an application layer gateway which violates and breaks the end-to-end principle. If we do this, for example, assume Lisa goes to smartgrid.epfl.ch to see what is the state of the grid. How many TCP connections will she use, or are there triggered by her activity on this figure? So let's see the solution. And the correct answer is 2. In principle, if you click on the page to go to the internet, you open one TCP connection. The reverse direction uses the same TCP connection. If you said 4, that means you assume something like FTP, where the web server opens a TCP connection to you to send the data. That's not done with HTTP. And there are 2, so one that goes to the HTTP proxy and another one. So that is how things work. In particular, on the internet, the IP address that we will see will be the IP address of the HTTP proxy, except if R2 is doing NATing, which is another side benefit of, another side reasons of those type of firewalls, is to hide all the IP addresses that exist internally. By the way, those IP addresses could also be private addresses, so it serves as an alternative to NATs. Voila, that's the end of this first hour. After the break, we'll talk of the very nightmarish topic of IPv4 versus IPv6.